the good part. I'm going to show you how to make the actual terrestrial planet material, and then after that, we'll look at the gas planet material. So, terrestrial planet texture. This looks pretty complicated, but it is complicated. You can kind of ignore this down here. In fact, I'm tempted to not even show it. But I'll talk about it briefly at the end, and let's just move these down here. I think it'd make more sense visibly if these are over here. All right, well, let's just go left to right. So there's some things we're doing here that are not really expected. So actually, I think the best place to start is going to be how we set up the material parameters themselves. So we have surface, opaque, default lit. There's one in particular that's very important. It's actually a couple. Where is it? Okay, this one's extremely important. This is usually checked. You need to uncheck it. Tangent space normal. Find tangent space normal. Uncheck it. That's required for your normal maps to look right. Everything else should kind of look like it is here. And that's really the only... I think I was experimenting with this, but this probably doesn't matter. Yeah, it doesn't matter. So flip precision mode can stay just default, but very important to remember to disable that tangent space normal here. All right. Whew. Okay, this is daunting to go over, but so we're calculating our initial texture coordinate here, and we're doing that by taking the absolute world position minus the actor position divided by the object scale. So this is our starting point for our texture coordinate. The next thing we're going to do is we're going to we have this noise offsets double vector parameter, and you'll notice it says XYZ scale. So this is going to control the offset of our noise on the X, Y, and Z axis along with the scale of our master noise. So we combine these three, make them into a float, and add them to our text coordinate that we calculated here. And that's going to form our just offsets that allow us to basically change what it looks like randomly. Then we have three layers of noise. You can see them labeled here. We have D1 noise, D2 noise, and master noise. So we also have this another double vector parameter, and this one is distortion 1 scale, distortion 1 amount, distortion 2 scale, and distortion 2 amount. So let's take a look at this. Because I just realized that this needs a space to be consistent with everything else. Okay, so take your texture. So we'll build the D1 noise first. So you take your texture coordinate that we just calculated over here, and we're going to divide that by the first channel here, which is our distortion 1 scale. So we're using this to scale independently our texture coordinate. This will then feed into our noise, and you may notice that we have two noise nodes here. That is because we wanted to be able to toggle between different types of noise, and these seem to be the ones that perform the best. So take a look at this. you probably don't need 10 levels of this, and this will make it faster. I will reduce it and see if it actually makes a difference. Yeah, it looks fine. So a 6, I think, is the default. That's for these is probably fine. Note the range, -1 to 1 here. Likewise, let's do 6 and -1 to 1. And then we have a static switch and a static bool parameter. This is flagged as distortion 1 type. Now this switch in particular will not compute anything that's connected that's not flagged. So like right now it's true, which means that only this noise is getting computed. This one's not getting computed. And if I flag this false, this noise is getting computed now, but this one is not getting computed. It's very important that this is a static switch parameter, a material expression static switch, and this is a static bool parameter, because if this is any other kind of like branching logic inside the material, it will calculate both, and it will be extremely resource intensive, because it's already resource intensive. Okay, so what does this get you? Well, let's take a look. The output of this will either, and remember this is negative, this is a -1 to 1, right? So there's variance in this black, you just can't see it. And if I flip this, let's see what it looks like. So just different kinds of noise. They're different shaped, they work differently. Okay, great. So then we run this into a multiply node, -1, to flip it. Since this is a -1 to 1, you can't 1 minus, you have to multiply by -1. Oh, hey, Space, I am using, this is Unreal Engine 5, is this application. It's free for anybody that wants it, you just have to download it and install it. But it's a high learning curve, but it's a lot of fun to learn. Okay, so we run the noise output here into this multiply node of -1, feed that into warp A, run the original value into warp B, and then we're going to connect our alpha channel of this warp node into this double vector parameter, specifically invert distortion 1. Now what's the point of this? This allows it so that we can, if we want to, flip, oh, I'm previewing the wrong node. If we want to, we can flip the output. So you see that, and you see that. That gives us variance in the types of textures that we can do. It's just more variance. Like we can run a partial flip or a full flip. You just don't want to run 0.5 because obviously the opposite of something merged half and half with that thing is just going to cancel each other out and you won't get anything. So you want something around the high end of 1 or the low end of -1 here to get good results. So it might look kind of familiar here because it's exactly the same thing, just slightly different. So again, we have our original texture coordinate that we calculated over here, and this time we're dividing it by distortion to scale from this vector 4 parameter. But the only difference here is this add node. Oh, I almost forgot. After this lerp, hang on, we go into another multiply node, and this node is connecting to distort 1 amount. So this is going to control how much this layer of noise distorts the next layer of noise down, right? So this is essentially saying we're going to multiply it, we're going to add it in at 10% of its value, right? So we have this, start previewing the node. We're taking this value, we're taking our scaled coordinate, and on the output of that scaled coordinate, we're adding this value to it. That's what's going to give us our distortion. We then take this value and we feed it into the position of our two noise nodes, gradient texture based. I'm bringing these levels down to reduce shader complexity because it doesn't seem to make a large difference. Gradient texture based on top, Voronoi on the bottom. Again, we feed those into a static switch. Gradient texture based on top, Voronoi on bottom, and then distortion noise to type, static Boolean parameter, just like up here, feeding it into the switch. This allows us to toggle between different types of noise. So real quick before we do anything, let's make our distortion 1 amount 0, and we can see what the actual effects are. So let's start previewing this node. Okay, this is what the node looks like with no distortion. And this is what it looks like with distortion. So there's Spaceman. There's the concept of procedural noise. Is basically if you ever use Photoshop or anything like that, it'd be like their clouds function or their noise rendering functions. It's basically creating a random pattern of black and white values that are they fall in different patterns based on what type of algorithm you do it in. You can see these noise nodes here. We have gradient texture base and Voronoi. So those are just two different types of procedural noise that you get on nodes inside the Unreal Editor, Material Editor. So we can see the immediate impact of adding this value that we calculated up here to the UV coordinates of this value, or these noises down here, by just turning off distortion, turning on a little bit of distortion, turning on a lot of distortion. This is what provides our like fine detailed variance and stops it from looking like a bunch of dumb clouds like this. So we'll go back to the value we had at default. Okay, this is the same thing. We have these two noises of our second layer of distortion noise fed into a switch with this static bool parameter. The output is multiplied by -1 and then warped with the original output, and our alpha is going back to this vector double vector parameter, the invert distort 2. So let's take a look, start previewing this node. So if we wanted to invert this, we can. It's just it's a way to get more control over what's going on in all this randomness, right? Finally, the output of this node goes to another multiply node, and this time we're multiplying by the distort 2 amount right here. Okay? We're doing the exact same thing. So we can think of this as our distorted distortion map, right? And then this number is how much this distortion map is going to distort the actual noise that we're going to use as our height map. Okay, great. So finally, we come down here to our master noise. We have our original texture coordinate, just like the others. We have a divide node, just like the others. And this divide node, you remember we had on our noise offsets, X, Y, Z, and scale. This divide node is connected to the scale property of that. And right now I have 100 in there. This is controlling the size of our master noise, like how big are your continents. The bigger this number is, the bigger your contiguous blocks of land and water will be. The smaller this number is, the more islands and small features you would get. So let's go down. So again, scale divided by our original modified UV coordinates. Again, we're feeding it into an add node and adding the previous layer of distortion noise to this. Now there is a difference here. Each of these previous noises, if you take a look at them, are between -1 and 1. The final two noises that we're using are between 0 and 1 because we want an actual grayscale height map to be the output of this. So we take a look, 0, 1, 0, 1. Okay, great. So same thing here. We have a master noise type, feeds into a static switch, feed the texture-based gradient into the top, then Voronoi into the bottom. In this case, in the top two, okay, so these are attention to detail things. These two, to flip, we're multiplying by -1. And that's because those noises were scaled between -1 and 1. So to flip that, we have to multiply it by -1. But to flip the 0 to 1, we can't just do that. To flip the 0 to 1, we have to run a 1 minus node. So the output of the switch goes into a 1 minus here instead of a multiply, then into our alert along with our original value, and the alpha will connect to the third value, or the Z value, in vert master. So let's take a look at what that does. But because my C level is high, it's not like a 1-to-1 inversion, but if my C level is at 50% or at 0.5, then you would see exactly the opposite. But because the C level's up, it's not exactly the same. Actually, let's just do this for demonstration purposes. So 1, and you notice it's just the inverse, right? It's completely flipped, whatever. The C level is independent of all this, so obviously if you have your C level at 75%, you're flipping the height map. That's not going to be like a perfect mirror of each other anymore. It's going to be like you have different islands in different places because your height map is, a lot of it's underwater. Okay, finally, the output of this alert map goes into this saturate, and I want you to just kind of ignore this switch here and pretend like all of these pins were connected to the output of this saturate node. This switch I use to add the option to provide noise textures instead of using the procedural noise, but it doesn't look as good because my textures aren't as good, and it doesn't like it. The reason you would do this is it's way faster. It's way faster to sample a texture than it is to generate procedural noise. We're generating 3 layers of noise here, which is pretty expensive. We're also generating a normal map down the road, which is also expensive. So like this is an expensive material, but I mean it runs pretty good. Like I'm not particularly lagging. I know when I stream this, like it looks choppy as fuck, but like I'm not having, on my side, it's moving around smoothly. All right, so let's go back in the texture. So ignoring this for now, if you want to do this, right, this thing, it's just another static switch, and basically I recreated this whole thing that we just talked about, but instead of using the noise nodes to do it, I used texture samples to do it, and I plugged in my own rendered noise into those texture samples instead of rendering the noise like programmatically in real time. So we can just pretend like all of these nodes go here, or like this node is effectively this node, our output from our height map. And let's just take a look at what that looks like. Doesn't look like much, and that's because we're too far away from it. But you can see you get all this interesting variation and organic looking. It's important for it to look organic, right? Like you want it to look like it's something that could exist in nature rather than something that you threw together from human hands. All right, so let's take a look at what happens now. So we have this C level switch, and we have the output of our saturate node, or our switch node here. So we'll go top down. So we have a land height map section here. The output from our noises is going to, for the land height map, go into the value. Our sea level scalar parameter is going to plug into the minimum specifically for the land height map. The output of this, we run through a saturate node. We run it into a power node. This is raising something to an exponent. The power node exponent is going to be connected to this vector, this double vector parameter. Specifically, it's connected to the land height fall off field. What this does is for the land portion of our height map, it will push the coast out or in based on how big this number is. I usually leave it at 1. If you make it big, you have big coasts. If you make it smaller, you have narrow coasts. So that value right here, land height fall off, the first value, the red channel, is going into the exponent of the power node. Then we're running it through a clamp to make sure that we don't have any values outside the range, which I think is actually the same as saturate. Oh, because you may potentially, depending on what you're doing, need to like cut out the bottommost thing because like I was getting artifacts in the ocean. I'll talk about it in a second. Finally, we run this into the saturate. So let's take a look at what this looks like before we do anything else. All right. So this is what's going to basically become our land height map after it's multiplied by the mask. If I can find it. Oh, no, it's the height map. Okay. This is effectively what becomes our land height map. Now, if we go down here, you see something very similar. We take the output of our noises, we plug it into the value here, but instead of plugging in our sea level into the minimum field of the smooth step, we're plugging the sea level into the maximum field with the minimum set to 0. That's one half of the equation that separates our land from our water. Then we run the output of that node through another saturate. We run it into a power node. The power node connects to the green channel here, which is sea depth extent in this double vector parameter that you'll have to make. Then we feed that into a clamp. And what I found is that when sampling these gradients, I would hit a point at 0 where the water texture would glitch out. So the reason this clamp is here is so that you can kind of guard against that. So this 0.01 will stop your water gradients from glitching out at 0. So we're just clamping it so that the minimum can be is 0.01 instead of the minimum it can be being 0. And then we're running that through another saturate. Let's take a look at what this looks like. So this is corresponding to like the variance that we'll see in our oceans. Okay, so then continuing down, the last thing that we're using sea level for right here is we're taking the output of our noises again, the same noises that we fed here and here. We're feeding that output into the Y field of a step node. This one right here. So we feed the output of our noise here, and then we feed our sea level into the X node of the step node. If we saturate that, we have our sea binary mask, and if we 1 minus it, we have our land binary mask. So let's take a look at those, because they should look kind of familiar. Okay. This is effectively a mask that we can use to take only the ocean areas. And this is a mask we can use to take only the land areas. We'll use these to properly divide between our two different gradient sample maps, so that you don't have any overlap or blending or anything like that between the water and land. It lets you do all kinds of stuff. All right, so now let's take a look at how we're going to use that in our actual textures. And I'm going to put a video out at some point showing the GIMP flow to create the GIMP assets, the like texture assets I've used to do this. This is very easy. GIMP is free. You can use Photoshop as well. Either way, but either way, it doesn't take long to make these gradients, and they provide pretty good results. So let's take a look. You're gonna want a texture object parameter here. I named it planet color gradient C, and then another texture object parameter here. I named it parent. I misspelled it. Planet. Misspelled it pretty terribly. I think I am mildly dyslexic, so cut me some slack. So we have our planet color gradient C and our planet color gradient land, and I'll just real quick, we can take a look what those look like. This is land, this is sea. Great. All right, so next we have our land, well, oceans on top, so we have our sea depth map. So we want to have a texture sampler. We plug in the planet color gradient C that we just made into the texture sampler, and then we have a make float 2 right here. The X value of this is going to come from your water depth map. The Y value of this is going to come from this temperature scalar parameter. So you'll need a temperature scalar parameter, and I'll explain what this is doing. Your height map is sampling this color texture right here along the x-axis. So the lower you are on your height map, the further to the left you are on this, and the higher you are on your height map, the further you are to the right, up until the point where you hit the highest you can for this, which would be your coastline, and then you terminate and you go to the next thing. The temperature, on the other hand, is controlling the y-axis. At 0, you're sampling from the very top, so you could think of 0 as being cold. And at 0.9, or it's actually 0.01, you're sampling at the very top. And at 0.99, you're sampling the very bottom. So why do we do that? Well, you'll notice this texture is pretty much the same. But notice that there's vertical variance in this gradient. So let's go to this. Okay, so here's our color map pre-multiplied by the mask. It hasn't been multiplied by the mask yet. This is our planet color gradient. So as our temperature gets colder, we're moving our sampler up the y-axis. Wait, is this the... oh, fuck. This is the wrong thing. Wrong value. Okay. Hang on. This one. So as our temperature gets colder, we're moving the sampler up the y-axis, and the bands that we're sampling out of this are moving into different seasons. For instance, at like a quarter, or like 33% or so, now we're in fall colors, right? And at 0, we're in winter colors. And at 99, we're in summer colors. And at like 75, we're in spring colors. So you don't have to do this. You could have just a regular gradient, but this allows you to have even more variance, and also you could animate the texture property if you, or the temperature property if you wanted to. You could have a slow sine wave animation looping through these temperature values, giving you like seasons over time if you wanted to animate it. Okay, so we were here. We have made a float 2. We've fed our height map into the x value and our temperature gradient and our temperature scalar value into the y value. Let's go ahead and make this 0.99 again. And we have our texture sampler here, which is spitting out the colors we want. But we may want to modify the colors after the fact, because it's very hard to like nail the colors in GIMP without seeing how they're going to look in Unreal. So that's what this next part is doing. We have this first multiply node, and you notice we have C brightness, C desaturation, land brightness, land desaturation. So let's take a look at what this is plugged into. Oh, wait. My mistake. This, so remember we build these masks down here, and they're, so let's take a look at the C mask again. It's masking out the thing. And remember, when we looked at this, it had all this color, this color here. Well, you don't want that, because you want to be able to cleanly combine this with the land later down the line. So what we do is we take our mask here that we made, which is 1 and 0. So the white parts are 1, the other parts are 0. That's what step does. We take this and we multiply it by our color output of this node. So we have another multiply node. We take the RGB, plug it in here. We plug in the A or the B. It doesn't matter. Multiply is, the order doesn't matter. Only subtraction and division matter. But so we multiply this by our binary C mask here. And now if I take a look at this node, so now we have zeroed out all the land. And this is good because this allows us to basically cleanly combine these two layers together later down the line. So next, we take the output of this node and we run it into a desaturation node, and our fraction here is hooked up to the green channel, or C desaturation, goes into this fraction. And finally, the output of that goes into another multiply node, and the output of this is being multiplied by the C brightness modifier. This allows us to have a fully bright C. Oh, I can't. Hang on. Stop. We can take a look at what these are doing, actually. So, fully bright, fully dark, right? 0.1, very dark, 0.2, 0.5. That works. So let's do very bright. And then desaturation, the higher this number, the grayer the colors get. So at 0, you have very vibrant colors based on your original gradient. At 1, you're in grayscale, and you can actually make the whole planet grayscale like this if you wanted to. It's kind of a cool effect. But 0.75, you have a little bit, it's like a steely gray. 0.25, you're more on the tropical side of things. 0.5, you're kind of like this kind of middle range. 0, you're just like fully saturated. So these are just ways you can tune the color independently. They're useful for achieving the look you want to get. We'll go ahead and take this to like a 0.5 like it was. So I'm at 0.5, 0.5, 0.5, 0.5, which is my default, but you can change them however you want. So the output of this is now your ocean color map. And this is going to go into an add node, which is why we wanted to black out the land. Because the next thing we're going to do, you could probably guess, is something very, very similar, but with a different gradient. So like here, we've loaded Terra C1, but here we've loaded Terra Land 1. So same idea. We make a float 2. We feed our land height map this time, not our sea depth map, but our land height map into the X value. And we feed our temperature into the Y value. And finally, we feed the result of this into the UVs for our texture sampler connected to our planet color gradient land texture object. The output of this is then multiplied by the land mask at this time. So let's take a look at that. And now you just have your land colors, but you have your ocean masked out. Then we run this through a desaturate node, and that's connected to land desaturation. And then we multiply it by land brightness. And our final color map for our land will look like this. So let's play with these a little bit. So if I go to 1, it's very bright. 0, it's obviously black. 0.5, 0.2, get it nice and dark. And 0, fully saturated. 1, fully grayscale. 2, weird colors. You can use this to achieve weird colors as well. But officially, between 0 and 1 are the values that you want to be working in if you want fine control over the colors themselves within the gradient. Otherwise, you're kind of like, who knows where you are, right? So 0.5, we'll just do 0.5 and 0.2 here. That looks like a pretty good land colors to me. So finally, you're going to take the output from your C colors and you're going to add it together with the output from your land colors. And that is what's going to give you your final color map with both layers combined together. Finally, this will plug into base color in our actual material. Now, we have the specular and roughness fields. This doesn't really require too much discussion. This is controlling how specifically shiny your water is, your water layer. Because the way we treat the height maps is different from the water layer, but you can actually change the specularity specifically of the water. That's why this says water shiny. You have water specularity, water roughness, and then we'll get to master luminosity in a second. Actually, we need to turn it up. Well, I'll leave it. So water specularity I've set right now at 0.01. water roughness I have set at 0.05, we take both into multiply nodes and we multiply them by the sea mask because we want the land to be fully rough. So we only want the shininess and the specularity on the water layer, and that's why we're multiplying it by our binary sea mask again. Again, we use this, we multiply by this when we want something that will only apply to the water, and we multiply by this when we want something that will only apply to the land. Makes sense. All right. Finally, the output of those masks, of those multiplied masks here, feed into the specular and roughness fields of the texture, respectively. Okay, next we have our color map here. We're going to do our luminosity gradients. So it's going to be a lot of repeating, you know, like this is doing the exact same thing up until this point as up here, just with different textures. So we have planet luminosity gradient C, planet luminosity gradient land. That seems familiar. We have a make float 2 plugged into the height map of the ocean, or the depth map of the ocean, and the temperature value plugged into the UVs sampling the C gradient. And we have, likewise, the height map of the land plugged into the X value, and the temperature plugged into the Y value, sampling the planet luminosity gradient land, going into this texture sampler. Finally, these are both multiplied by the binary masks that we talked about earlier, right here. So, again, this is just a white texture by default. I'll get into, like, I kind of went over what this does in the first video of the series, but I'll kind of get into what this does in a little bit. So what this allows you to do is to independently control the luminosity based on the height. And based on a gradient. So if you wanted to make a lava ocean, for example, which is something that we're going to look at, you can create your own luminosity gradient for the ocean, and you could have things like the deeper areas glow more, or the edges glow more. And likewise for the land, you could do something like, oh, only the highest peaks glow because they're volcanoes or something like that. So again, C luminosity, planet luminosity gradient C, fed into our texture sampler, multiplied by our C mask. Land luminosity, fed into our texture sampler, multiplied by our land mask, added together, and then the output comes into a multiply node, and the output is multiplied by this master luminosity field, the last one in our water roughness up here. Finally, we take the output of this and we multiply it again by our color map, because we don't want our stuff to just glow white. We want it to glow whatever color it already is. So like right here, if we take a look at this node, it's actually not going to be visible because it's so dark at 0.02. Let's do a 1. It's just white, right? And now let's start previewing this node. After we multiply it by the colors, though, we have the same colors we originally had. Now, this is the glow, right? So we don't want a 1.0. We want like a 0.01. And it's not going to be even very visible at all. But what this does, when plugged into the master materials, or the material output node's emissive color, it creates logic. So if you are looking at the front of a planet, right? Wow, the lighting really... What the fuck is going on with the lighting here? Let's turn off the preview scene. Land brightness. Sea brightness. Let's just make it bright to start. Okay, there we go. So you notice that like here we have the bright side, and then here we have the dark side. Well, this is too high, and our lighting is not from a single source. But basically what this value will allow you to do is, I may have to show it in the actual scene. Oh god. I'm going to go out of the scene and show it. It's giving us the ability to have the planet that's obscured in shadow show up a little bit. Or a lot of bit. However much a bit we want it to show up, we can make it show up that amount. So let's take a look. So you may notice that even though this side of the planet is shrouded in shadow, you can still pick out some detail on it. And the reason that's the case, if we open up our material instance here, hang on. Alright, we have this master luminosity field set to 0.005. So if I set this to 0, the black side of the planet is completely obscured in shadow. But you may not want that. You may want to be able to see it a little bit. At 1, it would be completely the same everywhere. The whole planet's glowing. Which might be something you want, but it's not something I want here. At 0, you have the natural lighting, but you can't see the backside of the planet. So like 0.003, we can pick out texture in the shadow, but we don't like it's still very clearly defined as a shadow. That's about where we want it. That way when we go to the backside of the planet, it's not just blackness, right? But you can still tell that it's a day and night division. Okay. That is the purpose of that. Let's pop back into our texture. So yeah, we're doing something similar with the luminosity gradients, but we're not applying the desaturation stuff to it because we're already accomplishing that in our color texture. What we are doing is masking them, adding them together, multiplying them by our master luminosity field here, and then finally multiplying them by our final color map here and feeding it into the emissive color. We're almost done. Maybe. Okay, next. World offset. So, if you look here, we talked about land height fall off and sea depth extent. I guess I could demo what those do. So, like, this is what I was talking about by this controlling the width of the shorelines. So, if I hit 2 here, we get more shorelines. If I hit 0.5 here, we get closer to the shorelines. That's what that value does. This value does the same thing, but for the ocean. If I hit 2 here, it gets darker. If I hit 4, it gets way darker. If I hit 0.2, it gets way lighter. And it's like the deeper part of the ocean pushing outward. The higher this number is. Right? All right, that's what those do. Now let's talk about what height scale and normal scale. And you may see that I added % of R. R standing for radius. We want these to be normalized by the planet's radius. That way we don't have to change them depending on the size of the planet, because otherwise this would be a static value. It wouldn't be relative to the size of the planet, and a planet that's 1,000 units with a displacement of 10, you might not even see the displacement. But a planet that's 10 units with a displacement of 10 would be bananas. Like it doesn't even look like a thing anymore. It's like it looks like a glitch at that point, right? So these values are how much do I want my height map to displace the land, at least for the height scale, as a function of the radius of the planet. So this was equivalent to me saying the highest peak that we're going to have can be 2% of the entire radius of the planet. So let's see, if I do 0.05, that would be 5%. And you can see, like, this isn't a very high polygon mesh here, but you can see that it's displacing much higher on the land here. But I find that 0.02 seems to be like right in the sweet spot of what you want. Finally, normal scale is also a % of the radius, but this is controlling shadows as if they were this would generate shadows from your normals as if that thing was this high of its radius. So like here it's like 0.5%, but let's do 0.01 and you can kind of see what I mean. 0.5 gets crazy, right? You don't want that. But 0.02, 0.01, 0.05, 0.005, all of these look pretty good. We'll do 0.0 1 to stick around here. Okay, so you have your height scale, percent of radius. That's this blue field here, the third one. And how are we doing that? So we come down here, we take this value, we have the object radius field. We're going to multiply this value by the object radius. We're then going to take our land height map here. We're going to multiply the output of this multiplication by our land height map. And finally, we're going to multiply that one more time by the vertex normal world space node. These are nodes you can just look up. Vertex normal world space, object radius. Okay. You just plug those nodes in. Finally, we're going to take the output of this node and plug it into the world position offset field of our material. Now here's the thing that I figured out a couple days ago, and this is really cool. So that's how we do our displacement. That's what actually raises things up and down. I had a heck of a time trying to come up with a way to generate normals procedurally. And this is what I ended up with here. So we're going to take our normal scale right here. We're going to multiply it by our object radius, which should look familiar because we just did it. We're going to multiply that by our land height map, which should look familiar because we just did it. And we're going to plug it into this node, the V3 of prepare preturb normal HQ. Prepare preturb normal HQ. I didn't know this thing existed till a couple days ago. So you plug this value, object radius, multiplied normal scale, multiplied by land height map. You plug it into prepare preturb normal HQ, and then there's another node, perturb normal HQ. Look familiar? You're going to take the first output of this and connect it to the first input of this. You're going to connect the second output of this into the second input of this, and you're going to connect the third output of this into the third input of this. So, what do we end up with this? Well, let's take a look. Alright, so what you're looking at is a normal map based on our height map. And this is what's giving us lots of like fine detail inside the continents themselves. Because without this, they would just look smooth. I mean, not smooth because they're displaced, but it wouldn't, like, you don't get this kind of like variance in fine detail if you don't run a normal map. So we plug that in to the normal node. And at this point, we've gone over every piece of the shader, of the material. I don't want to re-go over this. Just assume, like, if you get to the point where you've built all this and you want to swap it to use textures, there's a couple differences, but like the same concepts that worked here can be worked to do this with texture samplers. Maybe I'll come back and do that, but this doesn't work super great right now because my textures aren't good, so it's kind of like, whatever. Alright, so now for some fun. Let's take a look at how we generate these GIMP assets for this. So I pulled this up. Here's a basically projects. Hang on. Let me find my template. If it'll work. Lagging. Where's my XCF? Alright, this is fine. Planet, template. There we go. Okay. So basically to make these, what I would suggest you do is you go in and you set up a template. What I did is I made a new project that was, say, 200, well, in this case it's 400 by 2000. I don't think that's necessary. 200 by 1000 should be enough. You want to then create a layer for 25% on the vertical of each band. So like, and you may notice that I've named them summer, spring, fall, winter. So if I go to summer, summer's the hottest, it's on the bottom. Spring, second, next up on there. Fall, getting colder, closer to the top. Remember, when we're sampling from this, 0 temperature will be at the top and 1 temperature will be at the bottom. And finally, winter. So what you can do is you can go in, and let's take a look. And you can create, for example, you'll see this is called Terra Fall, Terra Spring, Terra Summer. This is like kind of a Terra Winter. It's kind of a graveyard of me like trial and erroring my way to this. So you can go to each of these layers and click this little button that will lock the alpha channel for that layer once you've made them, dividing it up into, in this case, 100 pixels each, but it'd be a quarter of whatever your space is. This is bigger than you need. So you're gonna go make 4 gradients if you need it, 1 for each season. So think about what colors you see in the fall. Think about what colors you see in the summer. Think about what colors you see in the winter. Think about what colors you see in the spring. Let's take a look at what a couple of these gradients look like. Here's Terra Fall. You have at the bottom, this is your coastline, going up into some darker text, into like some very light green, and going into like a more reddish color that you might see on like trees and such. And then finally, we have a little layer of snow creeping in at the very top. Likewise, if we look at Terra Winter, the greens push closer to the shoreline, and the snow has extended greatly unto about 50% of the gradient. So you do one of these for each temperature band. Let's just do it, right? Turn this off. Terra Winter. So I also set up guides on the side of these. You can just drag these on, but I line them up so that it's very easy for me to drag the gradient in a perfectly horizontal fashion. So I'm on the winter band. I'm gonna click this, move it over here, and then I have a band, right? And then we'll go to Terra Spring. We'll go to the spring band, do the same thing. There we go. Then I'm on fall. Drag it across. There's our fall band. And then I'm on summer. I don't know where my summer gradient went, but we'll just use spring again because it's pretty close. And this is really just for demonstration purposes. Alright, so we use spring a second time, but I would have a separate band for summer as well. Alright, so once you've done all this, you have your set of gradients to use as like one type of land. So what we can do is we can then layer new from visible. This will collapse all of that into one image. We'll drag this up here, and then we can turn this off. And then the last thing that you need to do is filter, blur, Gaussian blur. Now, normally you wouldn't do this when you're Gaussian blur, but in our case, you're gonna unlink them, set this guy to 0, set this guy to like, it depends on how big your image is vertically. This one is 400 pixels, so like a 10. And let's see how that looks. No, that's too little. So like a 30. Okay. You do this until you get like a nice blend between the bands. And once you got that, you have one of your gradients, you can export this and start using it. Again, these are the gradients that you load into, in this case, planet color gradient land. Now, to do this ocean, you do the exact same thing. It's just that with the ocean, a lot of times you won't have a lot of variance between seasons. Although you can do things like have some ice cover on the oceans during the wintertime, or have more tropical colors during the summertime, and then go to like grayer, more subdued colors in the wintertime. So you can make it change. It's just not as important. Usually you're not using it as much. Okay, now the last thing that we'll show, because this is fun, the last part of this texture is I'm just going to show how these luminosity gradients work with an actual like, because right now we just have the default luminosity gradient here, which is just white, which means that our luminosity is just going to be a flat value of whatever's set here, which is why we can say, oh, we're going to have like 1% brightness so that you can see a little bit of the dark side of the planet. But what if we had something like a lava planet where we wanted the ocean to glow but not the land? So that's where these guys come in. So I happen to have some lava textures. So let's grab the lava sea here. And let's grab the lava land. Alright, it's a lava planet, but it doesn't look particularly lava-like to me. Now, part of that is the fact that it's fully desaturated. So let's undesaturate it. Although I did kind of like some land desaturation. 2.5. Alright, so now we have a lava planet. We also probably don't want any water specularity. Or no, we want full roughness for lava, because there's not going to be like a shine on the lava, maybe just a tiny bit, but most likely you would have full roughness so that you don't have that shine. But I'm going to leave it because I'm just putting this back on Terra after I'm done showing it off. So I'll go back to 0.5. Okay, now if you want to make a planet that has separately, independently glowing parts of its structure, you will need to make another gradient the same way we just did, except this gradient will only be in grayscale, and the brightness of the gradient represents how much it glows at that height, from left to right, bottom to top. So let's take a look at lava, and you'll notice that I have lava land luminosity here and lava sea luminosity here. Let's apply this. And this. So now it looks the same. Why does it look the same? Because we're still at an extremely low master luminosity. But with lava, we don't want to be at a low luminosity. We want this shit to glow. So at 1, I don't know if you can tell, but we're glowing a little bit. And the most important part of this isn't necessarily the fact that it's not like putting off actual light, but the way it behaves with shadows. So imagine seeing a lava planet in space and you go to the backside of it that's under shadow. You would expect to maybe see the lava ocean still, but maybe not the land. So let's take a look at what this would look like. Yikes, is that still loading or something? I've made a mistake somewhere. That ain't right. Let's get rid of the clouds here. Is this might be, there it is. Okay, my black body was too big. 10.01, 10.03. Okay, good. Alright, so in this case you get, even though the land is dark on this side, you can still see the glowing oceans, right? And that's why, and also they glow at different intensities, and that's why we have this master luminosity field. So you can control it to however much you want. and in the shaded parts you'll still see the lava lakes. Whereas if this was the temperate one without the luminosity gradients, you would either have like a flat value for the whole thing, or you wouldn't be able to see it at all. So yeah, I think that's about it for this texture, or this material. I understand that this is quite a lot to take in. So maybe I just zoom in and show each portion of the mapping here. And anybody that wants it can just pause it at separate points in time and snag the logic to build it. Just remember to forget about this switch and just connect all this shit directly to this node, and you'll be in good shape. If you want this, this is how you add the texture sample version. It may still need some work. No, I'm not vouching for this. And then finally, where everything connects. And the full picture. Alright, and that's it for that. And the last thing that I'm going to have to show will be another video, and that's how to take this similar logic here and make this gas giant texture or material. So let's see, planet. Let's send it back to our texture instance. And once you make these texture instances, you can just switch back and forth between planets on the fly all you want. Hang on, I'm gonna real quick. I do like using the Terran planet as the baseline. So real quick, let's flip this back. Default luminosity. And then finally we change our master luminosity way lower, 0.5 or something like that. Oh yeah, and our saturate and desaturation values. That's why it looks so bright. I was like, why does it look so bright? It's because our land is way brighter than we normally run it. Oops, that's ocean. I think by default I was running 0.5. I'm missing something here. Oh. I see what I did. Notice that this says planet color gradient C and it has the land loaded into it. Oops, see? My mistake. That would be why. There we go. That looks more familiar. So even up close, I mean, it's like, obviously it's not going to be as good as like an artist that goes in and like makes all this shit by hand and spends hours upon hours doing it. But also, I can make like 100 of these planets in the time that takes to do one. So that's good too. And also, you can proceduralize this. Down the line, I intend to make a blueprint that combines all this shit together and can take, and then I can create a proceduralization wrapper around it to basically take a nugget of randomized information and use that to create a bunch of different planets just on the fly. And you won't know what you're going to get until it spits one out. But yeah, so this is definitely the most complicated one of all the puzzle pieces that went into making this. I'm kind of happy with it. Like, I wasn't expecting it to turn out quite as well as I think it did. Still have a desert atmosphere. Let's change it to something a little bit more earthy. A little bit more Earth-like. Maybe like... something like that should be fine. Turn our claws back on. And there you have it. Alright, so I'm going to cut it off here. This is the most important piece out of all of it. Oh, the other thing, before I forget. The object that you apply this to, the world height offset, I haven't figured out a way around it. I'm sure there is one, but it produces janky shadows. So the actual static mesh actor you attach this to, turn off cast shadow. You're going to let your normal map do your cast shadows for you. And also remember to turn off that tangent parameter in the material parameter, because otherwise that procedural normal map will not work. So you get your cast shadows on the surface from your normal map, and then when you turn this off, you will lose your shadow on things like rings and other things around the planet. Like you wouldn't be able to have an eclipse at that point or anything like that. This luminosity value is way too high. 0.005. Great. So what you have to do, take your planet sphere, clone it, make it a little bit smaller. Now you see this guy's at 10.05. I cloned it, made another sphere. It's at 10.03. And all this is, here's the material. That's all you gotta do. Take this, go in, change it to unlit. You're done. Save that as a material. Apply to the sphere. The only point of this is to throw a shadow. Since we've turned off shadows from our planet itself, it's not throwing shadows anymore. So if we want shadows that make sense for the planet, we need something else there to throw a shadow. So we just have this sphere on the inside of it with a pure black texture, and all it does is it's literally just there to cast a shadow on whatever's around the planet. And okay, that's it. I end it here. There's one more of these videos I'm gonna do, which will be how to build the gas giant, which we can take a look at, which is admittedly glitchy, but it does look okay. It's just there are some glitches with the way the translucency interacts on the gas giant. But that said, I can show you what it looks like before I hop off. It looks like this. All the animation speeds I have on these things are tuned way, way over what you would actually set them to For testing purposes, it doesn't serve me any interest to have the animation speed realistically low on like the cloud cover on a gas giant or something like that, because it just takes too long for me to actually tell if it looks good or not. So I ramp it way up, and then when I actually wanted to use it, I would ramp it way down. But yeah, this is the gas giant